Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 49. Today we are going to discuss on the nonlinear time domain panel method. It is a continuation of our previous discussion, okay? And these are the keywords that we are going to use to get this lecture. So, let us start. Now, if you remember that in the previous lecture, we stop at a point that we need to find out that Fruit-Kirchhoff pressure, a Fruit-Kirchhoff force over the nonlinear weighted free surface. When we talked about the nonlinear weighted free surface, in last class we have discussed, we are actually going to get through the incident wave potential, the exact free surface because of the incident wave potential. To be very frank, if you want to modify further, like even if the incident wave potential is not sinusoidal in general, it is not linear. Again, under the assumptions of the linearity, when you talk about the exact weighted free surface, we are in fact able to modify further the statement as follows, that that it should be we can further modify the statement as follows, it is exact weighted linear free surface. Okay, it is not exactly the actual ocean. Now, that is what actually it is written over here in the presence method. The Fruit-Kirchhoff and hydrostatic forces are calculated over the time variable exact weighted surface, that is up to the incident wave surface. Okay. Now, here also even if I do that, we have a problem, because in under the assumptions of the linearity, we really under the assumptions of the linearity, we really cannot go beyond z equal to 0. Okay. So, this we have repeatedly we told that the Green's function g, you can use the Green's function g only when you are using the linear free surface, that is z equal to 0. Now, if you even take it is z equal to z equal to eta x t, in this, even if it is a linear free surface, still you cannot apply the g. So, therefore, when we are actually calculating the phi, it is not possible for us to calculate this phi on this surface. We can always get this phi on this surface. However, what we are going to argue is that we can calculate the pressure because of the phi I on this surface with some modification. Now, how we do that? There are three classical approach we can discuss. One we call the hydrostatic approach, one we call the stretching corrections, one is called the unmodified formula. Now, in all, like we need to understand how we can calculate the pressure above the mean free surface. Let us now discuss when we talked about the pressure integration above the mean water surface, what I mean. Now, let us draw one picture. I have this, and now let us try to superimpose, just draw a linear waves. So, you can call this is trough, this is crest, this is trough. So, now here let us try to find out about the Fruit-Kirchhoff pressure. Now, you know that you have this expression phi equal to A g by omega into e to the power k z into sin k x minus omega t. Now, pressure P is nothing but minus rho del phi del t. Now, if you do minus rho del phi del t, then omega will cancelled out, then it is minus and minus plus, right. It should be a g e to the power k z into cos k x minus omega t, and of course, we have a rho, right. So, this is my phi. Now, if you look at it, it is driven to the e to the power k z. So, this pressure term is driven to a term called e to the power k z. Now, z is negative below the free surface. It is z equal to 0. So, when z less than 0 and then is the below the the water, and when z greater than 0 it is the above mean water surface. Now, if you look at it, this expression, the pressure expression actually driven by a exponential function. So, therefore, suppose this is my z equal to 0, this is the pressure term. Now, if you put z equal to 0 and remember that at, let us take that maximum pressure. So, cos k x omega t at crest it is value takes the value 1. So, this term goes to plus 1. So, eventually you have this term at z equal to 0, it is nothing but rho into a into g. So, this point, the value of this point is nothing but rho a into g. Okay. Now, since this driven through e to the power k z at z equal to 0, e to the power k z equals to 1, right, because e to the power 0 equal to 1. So, then value remain rho into a into g. Now, here it should drastically reduce as a exponential function. So, this is the graph below z equal to 0. Now, above z equal to 0, what would be the the pressure? Now, here if you remember, I said that there is a 3 method. When this unmodified formula, if you use this, it means that I really do not change this formula, I use the same formula above the z equal to 0 also. So, therefore, if you go through this, then this e to the power k z is now continuing above the mean free surface also, and therefore, it goes like this way, something like this. Now, so then in that case, this is actually my the pressure at free surface, right. Fine. So, this is called the unmodified formula. Now, when you use this unmodified, so there here actually it is not realistic. Why it is not realistic? Because since it is driven by e to the power k z, then for the steep wave, this value of e to the power k z at this particular point, let us say it is z equal to some positive, let us say even this some let us say 2. Okay, let us take that z equal to 2 this point, then value could be e square, some large values. It is so for the steep wave, this really gives very unrealistic value. So, unmodified formula really does not help much. Then let us talk about the hydrostatic approach. Now, this hydrostatic approach actually little bit consistent as well. Why? Because the hydrostatic approach says that we are using the concept of linearity. What is the concept of linearity? Concept of linearity says what is happening at z equal to 0, the same should happen at z equal to eta. Now, at z equal to 0, my pressure is rho a g. So, at z equal to eta also it should be rho into A into g, where A is nothing but my amplitude of the incident wave. So, therefore, the pressure value what is here, the same pressure value is over here, and then now this is basically my graph for the incident wave potential pressure graph. Now, let us why it is consistent, let me tell you. Now, if I look at the hydrostatic approach. So, now if I try to apply the hydrostatic pressure over here, now at z equal to 0 the hydrostatic pressure is 0 and then it is linearly coming down, right, and with the formula rho into g into z, right. Actually it is minus rho g z. So, when z equal to negative it become positive. So, that is why it is in this coordinate, right. So, hydrostatic pressure P equal to minus rho into g into z. Now, in a below z equal to 0 it is negative. So, it is positive. Now, what is above, then what is the point, I mean what is the value at z equal to eta equal to a. So, at z equal to a and a is positive, right. So, minus rho g z will give you minus rho into g into a, right. So, then this is the value you get the hydrostatic pressure at this point. So, it is minus into rho into g into a, right. Now, you see why it is consistent, because at free surface the total pressure should be equal to 0, that is our dynamic condition. Now, my static pressure gives my the value rho g a, the dynamic Fludt-Kirchhoff pressure gives the value plus rho g a, and if you add these two you will get 0. So, it is somehow it is consistent at wave crest. So, people are so this is the hydrostatic approach. So, what is hydrostatic approach? When you have so now hydrostatic, let me now just draw is the total pressure, just change the color. So, hydrostatic approach is above mean free level, the total pressure. So, hydrostatic approach cannot distinguish between the what is the static pressure, what is the dynamic pressure. This simply tells you what is the total pressure together with hydrostatic and the dynamic. So, therefore, when z is greater than 0, it follow this line, right. So, that means when z greater than 0, that pressure is follow rho into z into, now we can call it is you can say it is z minus a, something like this, right. So, this is when z greater than this thing. Now, you can see it is very it is actually consistent also, right. So, and then after that when z less than 0, the value that of the value p should be minus rho del phi I by del t, which is the this graph, and then together with plus rho into z into z, which is the this part. So, this is the hydrostatic approach. We have two component, one is above mean free surface, one is below mean free surface, right, and when is above mean free surface it follow this straight line minus rho, it started with minus rho g s and end with rho g a here, and after that it if you add these two, then actually the, so that total pressure graph look like somehow like this. So, this is the non-linear pressure plot, okay, for the non-linear Fludt-Kirchhoff force, Fludt-Kirchhoff pressure. So, here when you do the non-linearity, you really cannot split out the static component and the dynamic component above mean free surface, but the below mean free surface you can of course do that. And now the stretching algorithm is it is just extension of these things. Okay. Here if you do this now in case of a bottom actually now when in case of a trough, we really do not do this, we really do not use this idea that what is happening at z equal to what is happening at z equal to 0, same thing happening at z equal to minus eta. Here we are assuming that what is happening at z equal to 0, the same thing happening at z equal to eta. So, that is why in the free surface also we are taking the value rho into A into G. However, in hydrostatic approach when you below z equal to 0, that time we do not use this upper part, we do not use it, we can only use the lower part. Now, here is the difference between the this hydrostatic approach and the stretching algorithm. In case of a stretching algorithm, we are assuming what is happening at z equal to 0, the same thing happening at z equal to minus eta also. So, that if you apply this stretching algorithm, then it is consistent at crest, it is consistent at trough. Now, when I say that consistent the crest means that at crest that at free surface the total pressure equal to 0, and here also if you use the stretching algorithm similarly at this point also it is 0. Why? Because we are assuming now let me discuss why it is 0 here also, which is not for the hydrostatic case. Now, here if I draw the crest, now here now if you consider the hydrostatic approach, since it is z less than 0. So, at z equal to 0 at crest it is minus rho g a. Why it is minus rho g a? Because in this at the crest that cos of omega t that is equal to minus 1, that is why. In crest cos omega t equal to plus 1, and in case of a trough the cos omega t equal to minus 1. So, now it is as it is goes like exponentially down, and then in the hydrostatic also it is the linear like this. Now, if you see that at this point the value is rho g a for hydrostatics. Now, in case of now we are not using the stretching algorithm, we are using this graph and it is decay exponentially. So, at this point this value is less than minus rho g a. So, therefore, we have an anomaly in case of hydrostatic approach, but we ignore this anomaly because it is a single point. However, in case of a stretching algorithm, if I use that what is happening at z equal to 0, same thing is happening at z equal to eta. So, then actually this becomes the plot of the dynamic pressure. So, then at this particular point that value should be minus rho g a, and so therefore, if you do the addition it becomes 0. Now, at this point I must tell you one thing, that whether you are using the hydrostatic approach, whether you are using the unmodified formula, whether you are using at the stretching algorithm, nothing is very much justified by the fine and sophisticated mathematics. It is simply some kind of a technique that actually we are using to get somehow the nonlinear portion of the Fruit-Kirchhoff force. Okay. Now, if somebody tells now is it is mathematically sound, it is mathematically well justified, it solves this, I mean all these things actually the answer is it is not. Okay. However, as an engineer we are trying to modify the reality try to replicate the physics with simple mathematics. So all these three method is somewhat not very sophisticated in the mathematical point of view, but it is very practical, especially the hydrostatic approach. Okay. Now, here let us do one more thing, that in this nonlinear formulation, if you remember what is my boundary condition, this boundary condition is which is del phi del n is nothing but equal to V n minus del phi I by del n, and this apply at z equal to S 0, that means the mean weighted body, right. Now, if it is so, now I am using a nonlinear approach. Now, here initially if you remember that our level 1, level 2, level 3, level 4 approach, if you see our previous lecture, in level 2 approach what we say that we do phi linear and then phi I it is non-linear. That is what we discussed, right. Now, here let us now introduce something not level 2, not level 3. So, we can call this a level 2.5. Now, level 2.5 what we are doing? Now, what we are trying to do here, it is very interesting thing. We really do not want to disturb the framework of the linearity. We really do not want to disturb the framework of the linearity. However, we try to impose some kind of non-linearity in this equation, so that we can get some nonlinear effect in the component of the phi also. Okay. Clear? So, here the idea is we do not want to disturb the framework of the linearity. So, that means that we are doing z equal to 0, we apply here S 0. However, here we try to impose some kind of nonlinearity into the second term. Now, how it is possible? Again I am telling you that there is no much standard sophisticated mathematics behind this sort of approximation or ideas. However, it is coming little bit of some sense of physics. We try to do some analysis and try to see that if these effects are really effective or not. Okay. Now, here if you look at this this line, that what is said, that in the mathematical formulation the incident wave can be defined by a fully nonlinear numerical wave, which is absolutely the best thing that one should do, but here in this formulation we did not do that. While the perturbation effect are linearized, the boundary condition imposed on the mean weighted surface, that is what we are doing, like we impose the boundary condition at the mean weighted surface, fine. And here that F k force are calculated on the exact weighted surface. Now, we just discussed that how we can calculate the exact weighted surface, right. So, this is also this is actually our idea. Now, here we add one more thing, these all things are based on your level 2 computation. Here we just want to add one more thing, which is I try to modify the boundary condition to incorporate some kind of nonlinearity. Let us see how we do that. Now, you see now we are applying the boundary condition at z equal to 0. Okay. Now, suppose I have the wave. Okay. So, this is the pressure plot, let us say unmodified or modified, whatever. Now, what I am doing over here, I try to calculate, I have this value for phi. Now, remember that del phi del n, del phi I del n is nothing but grad of phi I dot n. So, let us say this grad of phi I dot n actually I plotted over here. Now, what is the grad of phi I? Grad of phi I is nothing but the velocity potential dot n in the normal direction, right. So, you can see that it is some kind of a push, right. So, physically what we assume that it could be some kind of a push, we are pushing something. So, we are getting this much of area and we are doing it at free surface. So, I am doing it at z equal to eta. So, I get this area. What I assume that we are mapping this area into the linear. So, what is happening here, I am getting z equal to 0. So, what I am doing that this area and this area should be same. Now, if this area is the same, then what would be the value for C? I am assuming this pressure graph, you know, this phi is nothing but a g by omega into e to the power k z, it is driven by e to the power k z. So, therefore, this curve also can be written as let us say this curve, I write this curve should be written at some c into e to the power k z. Now, if I know the value of c, so then if I integrate this value, so this area and this area should be the same, that is my idea. So, then what actually I am equating? I am equating the total push by the phi I should be same. So, that push I distributed over another hypothetical curve which is c into k z. So, total grad phi del n is now it is changing to this. So, the only objective how I get this value c. If I know the c, so then I know this curve, let us call this curve A is nothing but c into e to the power k z, and this is nothing but the curve of my modified del phi del n. Okay. So, then since from this curve I can get that value of del phi del n at any point, right. So, that is what actually our idea. Now, to do that, what we are going to do is that we are equating the area. So, now I calculate that grad phi dot n over this length, I integrated from here to here. So, I get this area and then I equate this area with this. So, that is what I do. So, initially from minus d to eta, which is nothing but if you look at this, say this is your minus the depth minus d to eta, we integrate this value grad phi dot n. Okay. So, this dz dash in this dz dash it is basically grad phi dot n. So, dz dash is nothing but n dot dz. Anyway. So, we are getting this area and this area I am equating with this graph. So, I know the value of k, I know the value of z. So, now it is minus d to 0 and then minus d to 0 is nothing but my what is d? D basically in the ship, this keel point is nothing but my d. So, now I integrate minus d to the free surface z equal to 0. So, when you do this we equate this, I get the value of c. Now, once I get the value of c, so now I know my grad phi del phi by del n follow the curve c into e to the power k z. So, therefore, this boundary my del phi I by del n. So, now this del phi by del n now I can write as V n minus c into e to the power k z. So, this is now my modified body boundary condition. Okay. So, this is how actually we are incorporating the some kind of nonlinearity in the body boundary condition, so that I get some nonlinear value for the phi. Okay. So, in future lecture we are going to see that whether it really helps or not, that definitely we are going to discuss from our next classes. Okay. So, today we are going to stop here. Thank you.